One of the big arguments from those who are dubious about climate change is the idea that we cannot impact the entire planet. It's just too big. Well, let's look at something that did. Ozone depletion by man-made chemicals. It has been known since the 1970s that a whole host of compounds emitted by humans deplete the stratospheric ozone layer. Do you remember what ozone is? We talked about this in chapter on air. We have the ozone, we've got oxygen over here. He is O2. And then there's also another form of oxygen that's O3. Notice that she's bent. Right. And she's also, you probably can see, got one more oxygen in her molecule. Well, let's take a look at the role of ozone in our world. Here is what do they call it? Falsified coloring to show densities of ozone around the world. And you'll notice the different continents are easy to see, and then your eyes are drawn to Antarctica. Antarctica has the thinnest ozone layer, the greatest depletion. The units are Dobson units that it's not really important to go into that. But it has to do with the unique weather down there. One of the reasons that it's related to why it's also by far the coldest area in the world. So let's talk about what ozone is and where we'll come in contact with it. We'll see it in the stratosphere and in the troposphere. Now, when it's in the troposphere, it is not good for us. It is a lung irritant, a throat irritant. It aggravates asthma and emphysema. And kind of ironic, though, when it's up in the stratosphere, it is a protectant. It shields us from some of the most harmful UV radiation from the sun. So right now we're sitting in a time when we've got too much here and too little up there. It would be nice if we could take some from down here and put it up there, but that does not work. Okay, now let's take a closer look. Ozone amount is on the x-axis and the altitude's on the y-axis. And remember that we have these different areas of our atmosphere, and above the stratosphere is the mesosphere, but by far the most molecules are in the troposphere. That's where we spend our lives. And we can see the ozone's increasing from pollution. Primarily it is, remember it's a secondary, so primarily it comes from the NOx mixing with volatile organics and it happens a lot in the summer because it is its production is helped by the presence of the sun. And then we have the ozone layer up here in the stratosphere. And here's just some relative heights. The total mass of ozone, about 3 billion tons, about 10 to the minus 5% of the atmosphere. So it's not a lot of the atmosphere, but oh my gosh, what it does is of vital importance. Without the ozone layer, the Earth would be sterilized by the high energy UV radiation from the sun. Okay, so where is it? Well, it's been measured since the 1970s, and it goes as high as about 15 parts per million in the ozone in the stratosphere. 91% of the Earth's ozone is there. It is surprisingly small if you put it at ground level pressures. 1 atmosphere, 760 millimeters of mercury. It would only be akin to a liquid about an eighth of an inch thick. The total concentration has been measured for many years, and they start seeing a dramatic decline. The depletion far exceeds the natural variability and has occurred without exception since the 1980s. Man, it got so low in 85, scientists thought their instruments were malfunctioning all over the world. And where we see it, the thinnest is in the ozone, and they call it the ozone hole, and it's the clearest manifestation of the effect. This ODS means ozone depleting substances, and let's talk about that a little bit later on. The ozone hole is actually, it's not totally a hole, it's just a thinning, a very thin thinning. And that's the Dobson units again. Remember, at their peak, we see them up around 425 or 450, so this is about half. The largest Antarctic ozone hole ever recorded occurred in 2006 at the size of about 10.6 million square miles. That's about 3 times the size of the United States. So you get an idea of how humongous this is. It was first discovered in the late 1970s by the first satellite mission that could measure ozone. It was that noticeable. The hole has continued to grow steadily during the 1980s and 90s, though since early 2000 the growth reportedly has leveled off. Even so, we're going to see it varying from year to year, and it's not going to go away for a very long time. I don't want to tip my hand, but the thing that's causing it ain't going to go away for about 100 years. So, all right, much lower than levels predicted by the natural Chapman cycle. Now, the Chapman cycle is a cyclical set of a mechanism of, it's a set of chemical reactions in which O2 is broken apart into oxygen atoms by the sun's radiation. Then the oxygen atoms hits O2, our natural, very stable form of oxygen. That way it becomes O plus O2 to become ozone. Then the ozone's hit by radiation, principally very high UV radiation, and this guy breaks him back to O2 and O. So you can see it's kind of a cyclical set of steps. And then what we're finding is that in the natural state, this is a steady state. In fact, no net change of O3 is seen. It undergoes decomposition, but it's also reformed. That's why it's called the Chapman cycle. All right. Now, the problem is that we have perturbed the natural condition. Now, why is it Antarctica? Look at the temperatures here. This is the Arctic winter, the Antarctic winter. And since they're on opposite sides, they have the opposite 6 months. Notice that. Hey, yeah. And September is, let's concentrate on Antarctica. This is called the spring. But in the winter time, oh my gosh, look at the degrees. This is Fahrenheit. Oh my gosh. And it's the range of values, but look at these. This is Antarctica is so much colder than the Arctic. And you say, why could that be? I think once you get below 100 minus 100, it's all a moot point, but geez Louise. Okay, so the reason being is that Antarctica has these clouds, and the wind circulates to form a vortex, and this vortex prevents any warm air from entering the region. And inside this vortex, clouds form. And on these big, large, and pieces of ice in these clouds, they also help the chemicals that are depleting the ozone become more active. So that's why we see the ozone hole, the greatest in Antarctic. Let me get this to you straight, though. The ozone thinning is occurring globally everywhere around the world. It's just really seen in the Antarctic. Okay, so here she is. This is September 4th, 2012. So this was a recent event. And can you see the blue and purple colors are where there's least ozone. The yellow and reds are where there's most. Look at, they're right next to each other. Again, this is this weird wind situation happening over the Antarctica. And there's my little friend Antarctica. And here is the bottom of South America, Tierra del Fuego. And you could probably, if you tried real hard, you can find Australia there too, around the side. Okay, and here's just some numbers. Watch it go woo, up and down, up and down, up and down. And we're looking at minimum ozone, and it gets pretty thin. All right, so what's causing it? Well, Oh, before I get there, I have one more thing. It is changing the climate around there too, in all of the southern hemisphere. Ozone is a greenhouse gas, and its absence, together with the surface winds, has changed what's going on down there. There's observed warming over the peninsula. Holy cow, we're watching it rise abnormally high. That's a new study that just came out of OSU. We'll talk about that later on. But there's also cooling over the high plateau, and this has also been one of those cherry-picking things where the climate change deniers said, see? Well, we shall see ourselves. The changes in wind have also been linked to regional changes in precipitation. We're getting increased sea ice around Antarctica, warming up the Southern Ocean, and local decrease in the ocean sink of CO2. The solubility of CO2 in water is temperature dependent, so if it gets warmer, it holds less gases. That's just a way it is for everything. Here she is. The Antarctic cooling controversy relates to questions posed in the popular media regarding how can there be temperature increases if it's going down some places. That shows a definite lack of understanding of the complexity, but it is kind of strange when you see these blue areas right near these very red areas. This West Antarctica, that's called the peninsula part, that's gotten a lot hotter than expected even. This came out recently from OSU, thank you very much. It has increased about 4 degrees over the past half century, about twice as fast as previously estimated. And the problem is not just the temperature, but they're worried about ocean levels. Remember, this place is huge! Antarctica is a huge continent. So they're worrying about ice shelves. And you probably can't read that. It says the Ross ice shelf. These guys calve off. I think you probably heard that term. And they're all sitting above water level or sea level. So when they melt into the sea, they raise the sea level. Okay, but over here, and remember our Antarctica has these very high mountains too, we are seeing cool temperatures. But that is saying, remember, this is much bigger than the United States. This is that's kind of talking about one coast versus the other coast, and there can be big changes, obviously. Okay, so they tried to figure out what was causing it, and they looked at the ozone layer, and they looked at, stratospheric chlorine. Remember chlorine, Cl on your periodic table. And we watch as the chlorine went up, the ozone going down. Or is this causation or correlation? Well, this was a lot easier than CO2 versus temperature that we talked about before. This was causation. CFCs, which you've probably all heard of, chlorofluorocarbons, they're compounds made out of the chlorine, or chlorine, fluorine, and carbon. They are halogens, of course. This is group 7A. The most famous of which you may have heard of the freons. It's principally freon 11, freon 12. And they are virtually inert in the troposphere. That's because the troposphere is not being subjected to high energy UV radiation. And these guys were fantastic. These are one of the biggest success stories from chemistry. They replaced sulfur dioxide I've forgotten the other one, I'm sorry. But these were inert. I mean, they put them in inhalers, for heaven's sakes. They're used as refrigerant and air conditioner gases, spray can propellants, foaming agents. So it's seen as one of the greatest triumphs of chemistry, and it revolutionized air conditioning. Became very cheap and safe, and it is not unreasonable to say it's been a lifesaver for 50 years in the United States. There's lots of statistics about how many people die when it goes over 90 degrees for extended periods of time. And think about this. Air conditioning changed the entire socioeconomic landscape of the U.S. South and Southwest. All right, interaction with ozone, though. Yikes! First, I should have a comma here. First, freon, which is so inert in the troposphere, reacts strongly with the high-energy UV radiation available in the stratosphere. It pops off chlorine atom to create, and I do need you to know what this is. All right? Free radical is a very reactive species because of unpaired electrons. Okay. It looks like that. Hello. And then the chlorine attacks ozone in a complex series of steps. Just like the Chapman cycle I talked about before, this is a big old mechanism, and you do not need to know this at all. But just to give you an idea, I've got the single dot supposed to represent a single electron. And he hits my poor little ozone, and ozone becomes O2. And then he undergoes some changes, and the scary part is he's regenerated. Yikes. So he's consumed up here, and the stinker is regenerated. And that's why a limited number of chlorine atoms from our CFCs could be responsible for the destruction of a huge number of ozones. The overreaction, if you added this guy up, like these are mathematical expressions, you'll notice you can cancel them out and just keep going until you get this very simple reaction. We've referred to Cl as a catalyst, and I need you to know what this is. A catalyst is a chemical substance that participates in a chemical reaction and influences its speed. And here's the deal: without undergoing permanent change. This has made many. This has been responsible for the gainful employment of many a chemist, is to figure out better and better catalysts. So chlorine's consumed in the first step, but it's reproduced at the end of the second step. And so what does this mean? Well, on average, one chlorine atom can catalyze the destruction of as many as 10,000 O3 atoms. Swell. And there we have our little ditty from the book. Oh, for Pete's sake, let's just get some ozone and send it back up there. Why doesn't this work? Well, number one, it's a humongous amount of ozone. Even though it may be a small percentage of the overall atmosphere, it's a huge amount. Plus, it would be subjected to the Chapman cycle, and it would be also subjected to the Cl plus, or the Cl free radical, and it would be consumed. Response to the global crisis? Well, unlike the climate change crisis, the response to the ozone depletion was swift and decisive and swift. Well, maybe that's my problem. I called it the climate change crisis. Most people, not most people, but a lot of people don't see it as a crisis because it is not impacting them every day. This kind of did, because they could see it thinning with alarming quickness, and the end was in sight. And steps were taken to limit and limit the manufacture of CFCs. Since 1978, their use was banned. Then we have this Montreal Protocol, which is one of, can you imagine how hard it is to get the world to agree on something? And the Montreal Protocol, 80% of the world signed it. Of the nations signed it. India and China did not. I believe, because they thought it was unfair to developing countries. But it keeps going. It's been amended so that their more stringent limits were set in 1992 and the ban in 1996. And you can see when this was signed, and the amount of thousands of tons of the CFCs has dropped like a rock. And this is our stratospheric Cl plus levels. Okay. So, perhaps the most important feature of the ozone regime is the way in which it brought together an array of different participants in pursuit of common ends. Scientists have provided the information with steadily increasing degrees of precision on the causes and effect. Industry, responding to the stimulus provided by the control measures, has developed alternatives far more rapidly than initially thought possible, and has participated fully in the debate over the phase out. They also had substitutes. Here are the two that lasted until, I think they've been, they'll be phased out in the United States by 2015, and developing countries by 2030. Developing, I think they need a new word. We need a new word. I guess we can think of developing countries more as ones that have a long way to go to become mature mature markets, mature oh, fudge. Let's just drop that. Okay. Estimates to change in air conditioning equipment in commercial buildings in the U.S. are estimated to be about $2 billion. Used in goods valued at about $30 billion a year. These are known collectively as the refrigerant R410. And there's still a huge number of pieces of equipment that depend upon them. They would add these two guys together. You notice they took out some chlorine, added hydrogen or more fluorine, and that reduced their ozone depleting ability to 5%. 5% ozone depleting capability of CFCs. They also have only a 20-year lifespan. Versus about 100 for CFCs, which is another reason why they're so scary and why we will see the ozone hole stick around for quite a while. Now, these guys have been banned here, but not yet banned in many other countries such as China and Mexico. So there's a large black market. Smugglers making a lot of money. And the price of HCFCs 22 has, for this one especially, has gone up meteorically. Finding alternatives is an opportunity, but also a great expense. They're talking about taking out totally these chlorines and just using fluorine and hydrogen, and that'll probably be the next big thing. But those guys, oh gosh, it just never ends. They have the capacity to be strong greenhouse gases. So there's development that has to be done, and chemists have to work on this together with industry and government.